Hi, I'm Paul. We're doing Leetcode must-know interview questions, and today's challenge is flatten binary tree to linked list. Rating, medium. Well, okay. Given the root of a binary tree, flatten the tree into a linked list. The linked list should use the same tree node class where the right child pointer to the next node in the list, and the left child pointer is always null. The linked list should be in the same order as a pre-order traversal of the binary tree. Pre-order is root, left, right. Okay. Well, so here's an example. Binary tree. You want a linked list where all the right pointers point to the next node. The left pointers are all null. Notice that it is a pre-ordered traversal 1, 2, 3, 4, 5, 6, also known as a depth first search. Okay, you should know how to do a depth first search. In going through solutions like this, it's not really helpful to memorize the solutions or to try to memorize the solutions to Leetcode problems. If you memorize a solution to a problem, you can solve one problem. If you understand the concepts behind a problem, then you can solve lots of problems. So, we had, for example, a group of, you should know, for example, how to work with basic data structures and algorithms in your programming language of choice. So in Java, you should know how to work with linked lists and hash maps and, of course, arrays and strings. There are some concepts like two-pointer solutions or sliding window solutions or depth first search or breadth first search or recursion. If you knew how to do a binary search, that would be good. If you're feeling ambitious and you learned how to do dynamic programming solutions, that's good. Okay. So, they rate this as a medium, but because it's a depth first search, and really you should, if you're going to a coding interview, know how to do a depth first search. Let's just say it's on the low end of medium. Let me see if I can sketch through how we would do a solution to this. I'm going to have to make it a little bigger. All right, so let's try this. Depth first search done with a stack. Let's, on here I should have a pen. Hang on. Okay, I think I got it now. Depth first search done with a stack. So we're going to push the first node onto the stack. The first node, this will be our stack here. First node is a 1. All right, now we're going to go into a while loop until the stack is empty. All right. First thing we do is pop the stack. All right, I'm going to put the popped number right here, and I'm going to take it off the stack. If there is a right subnode, which there is, push it on the stack. Right subnode is 5. If there's a left subnode, push it on the stack. And there it is. It's a 2. If the stack is not empty, then the current, you know what? I should label that. C-U-R-R. Current pointer. The current right pointer will be, we'll do a stack peek, not a pop, but we'll look at the top number on the stack, and current right is going to point to whatever is on top of the stack. So that means 1 is going to point to 2. Okay, back to the top of the loop. Current, we're going to pop the stack and put it in current. So that means pop this and put it here. All right. Is there a right subnode of current? Yes. Push it. Is there a left subnode of current? Yes. Push it. All right. Is the stack empty? No. That means the right pointer of current is going to point to the node on the top of the stack. So 2 is going to point to 3. Okay. Back to the top of the loop, pop the stack again. So this is gone. 3 is what we're going to pop. And so 3 becomes current. Now what? 3 doesn't have right or left subnode, so there's nothing to push, but the stack, since the stack is not empty, current right is going to point to the node on the top of the stack, which is 4. So 3 is going to point to 4. All right, back to the loop. We are going to pop the stack. That means this is not going to be current anymore. We're going to pop the 4, and now 4 becomes current. All right. 4 doesn't have any right or left subnodes to push on the stack, but the right pointer of current is going to point to anything that happens to be on the top of the stack, which in this case is 5. Oops, I didn't mean to do that. Let me erase that mark. Yeah, okay. I can fix that, I think. All right, so 4 is going to point to 5. Okay. Anyway, I think you can see how this is going to play out. We're going to pop the stack. 5, we're going to push the 6, and then 5 is going to wind up pointing to 6. And what we're going to have here is 1, 2, 3, 4, 5, 6, just like it shows in the drawing here. Okay, so that's depth first search. Let's take a look at an implementation. All right, let me take a look at these constraints here. The number of nodes in the range is 0 to 2,000. Okay. 2,000 is not so important, but the 0 is important because it presents us with an edge case, which is that the root might be null. So if the root is null, there's really no point in doing anything other than returning. This does not return a value. It just updates the pointers in place, which is what we were asked to do, right? Flatten the tree in place. Okay. We need a stack. Java has a built-in stack. And we are going to stack what are called tree nodes. Equals new stack. And we are going to push the root. All right. Now for the loop. While the stack is not empty, stack has a built-in method for that. We will say tree node current equals stack.pop. And then we will see if there is a right-hand node on current. If current right is not null, stack dot push whoops. Okay, push the current node. I'm going to copy that. Also, if current left is not equal to null, we are going to push that. Good. If I can copy that. If the stack is not empty, then current.right is going to point to whatever is on top of the stack, which we can get using a peek method. And there's something in here about the left pointers all being null. The left child pointer is always null. Now that's not, we're going to have to set that. The one we did yesterday, there were certain pointers that were initialized to null. In this case, pointers are not initialized to null. So we're going to have to say current dot left equals null. And I think that's really about all there is to a depth first search. Let's try and run it. File error, not a statement. Oh yeah, I guess it would be good if I gave it a name. Let's call it stack. Okay, run stack push. Push cannot be referenced from a static content. Okay, hang on a second. All right, that actually shouldn't be capitalized. Try it one more time. Yeah, it always takes one or two little tweaks. All right, base case is accepted. Let's submit. See what happens. Yeah, that isn't really fair. I mean, so everybody gets 1 millisecond, but they only give us a beats 24.66. I mean, so I guess somewhere inside there. Oh, what? Really? 75.34 used 0. So it's kind of a rounding thing, but it's all very close. And as far as space, we're doing great. Let's get the memory. Okay. Because it did say 01 space. Do it in place, 01 space. So we're in great shape on that. Okay. That's it. Know how to do a depth first search. You use a stack. Also know how to do, I keep saying breadth first search, I think. Know how to do a depth first search. It uses a stack. Also know how to do a breadth first search. It uses a queue. Um, again, knowing the concepts is much more important than like being able to solve this one problem. So that's it for today. Please feel free to like, subscribe, comment, and see you next time.